This is a video about a concept in chemistry called equilibrium. Equilibrium is a new concept that we don't talk about in the beginning parts of chemistry, but as you move toward the end of the course, you'll find that most chemistry courses spend a little bit of time talking about reactions that don't go to completion. So what that means is most of the year, all year, we've been assuming that if we start with something like, let me rewrite that, if we start with something like zinc plus HCl, we end up with something called zinc chloride plus hydrogen. This is the reaction that we did when we made the balloons full of gas on the ceiling. And we've done it 2 or 3 other times in different ways for different purposes, but this reaction we've always assumed has an arrow that goes one way. So equilibrium is different in that sometimes you'll have an equation like this, nitrogen plus hydrogen, it makes a gas called ammonia. But if you change the parameters of temperature or pressure, then sometimes you can make the reaction go both ways. And so what that means is that the things on the right begin reacting to form the things on the left, and you always have a certain amount of what's on the right and a certain amount of what's on the left. Equilibrium does not mean that you have equal amounts. It means that the rate of change is equal. So equilibrium means rate of change is equal. And what that means is the rate of the forward reaction equals the rate of the reverse reaction. That's how fast it's occurring. And that happens in chemical equilibrium. It also happens in physical equilibrium. Like if you have, if you had a bottle, here's a bottle, and the bottle has water in it. You may have seen this. You got a lid on the bottle with a stopper in it. You got water inside. You may have noticed that sometimes you'll see little drops of water on the inside parts of the bottle up here, and there's water down here. The reason that happens is there's water vapor that evaporates from this water, and so the water that was liquid becomes water that's gas. But there reaches a point where you've filled all the available space with gas, and so some of the gas begins to condense, and some of it goes there, and some of it goes there, and then what goes here, some of that goes there, and you eventually get water molecules going in and out of the liquid phase at an equal rate, and that's called a physical equilibrium or a dynamic equilibrium, so that the rate of exchange between evaporation and condensation is the same. It does not mean that the evaporation stops and condensation stops when you hit equilibrium. What it means is that the rate of evaporation is equal to the rate of condensation. And it doesn't have to be here, it can be on the sides, and that's why you see the water droplets on the sides of the bottle. All right, so what's equilibrium mean? It means rate of change is equal. So I wanted to show this video, and we're going to watch this whole 6-minute video, and I'm going to stop it periodically. But this is a very nice demonstration of what equilibrium is, done by a teacher in a classroom in a different school. So here we go.
Okay, this little demonstration kind of helps us with the idea of equilibrium and reversible reactions. So what we see here, to start off, we have colored water, some green water here, that represents our reactant side of our process. And then of course we have our empty container over here that represents our product side of the process.
Okay, so these are the things on the left side of the arrow. This is on the right side of the arrow, and there would be an arrow right here if this was a chemical equation. So reactants are what you put in, products are what you get out.
So in any good reaction, when you start the process, everything's a reactant. So we all have all the water over here, and nothing is a product. When you have a reversible reaction, or a reaction that has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So on our very first scoop, if I'm using 2 identical beakers, if I go in here and scoop, on the very first scoop, all of it is going to be reactant turning into product, and none of the other. However, the very next time I scoop, some of my product is actually going to go back into my reactant side. Now if I continue to scoop like this, and continue to do this, you'll notice how at first the reaction ran really fast. And at first, a lot of water was switching sides, going to the product side. But then it kind of seems to slow down a little bit. And at some point, if I continue to scoop, the amount that I scoop going each direction will become the same. So if I look, I have 250 milliliters here. I only have 200 on this one, so I'm not quite there yet. Okay. So now if I have 250 milliliters here, I have 225, so I'm getting closer. So I'm almost at equilibrium. And here I have 225, 225. So if we look, and again, this is not perfect measurements, but if we look at our volumes there, they're almost identical, which showing that the amount that is crossing from here to here is equal to the amount going this way. Now,
Again, when we defined equilibrium a minute ago, we said that equilibrium is the rate of exchange. So the quantity that's going from
the
right to
amount
left
in
and the quantity that's going from left to right are the same. In this case, the water levels are the same in the two containers, but that does not have to be the case. But the rate of exchange must be the same for equilibrium to be established.
beakers represents the rate. Okay, so the rate of transfer is the same, so they're almost identical, which showing that the amount that's crossing from here to here is equal to the amount going this way. Now the amount in the beakers represents the rate. Okay, so the rate of transfer is the same. From here on out, I can do this for a day, 2 days, 10 days, 10 seconds. It doesn't matter. This is at equilibrium. Okay, so the amount I take from here goes here, the amount I take from here goes here, and that process will never end. So this reaction now is basically over. It doesn't mean it doesn't keep reacting. It just means it's not going to change anymore. So we've reached equilibrium. Okay, so if we go back to the graph on our slide, we would see that this is the first one, or the top one, where the rate flatlines and becomes equal. Okay. Now, it doesn't mean that we have to have equal amounts. If you look at our tubs, because I was using the same size beaker, the top one where the
Let's revisit this for just a second. So this on the y-axis, this graph has rate. And so at equilibrium, the rates are the same. But the actual amount of stuff does not have to be the same. This represents the amount that's in these containers. Now, lest you be confused, in this case, it is the same, but in the next one, it won't be. So here we go.
rate flatlines and becomes equal. Okay. Now, it doesn't mean that we have to have equal amounts. If you look at our tubs, because I was using the same size beaker, the volume level in the tubs are also very similar. So you'd almost get the indication that maybe the amount in each side has to be equal. So it has to be 50% this, 50% that. And that's not necessarily true. If we reset our setup here, and we begin again, but this time, instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as reactant. I'm going to use the little guy for my product side. Okay, so in our very first scoop, again, it's all reactant, no product. Again, I start scooping and I get some product back to reactant. Okay, now you might think there's no way you can get equilibrium here because the big scooper will always outdo the little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam here. Again, we're looking for equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at about 140 milliliters. So if you look, these two volumes, even though they're in different size containers, again, are showing almost identical volume, which
means what? It means the rate of exchange is the same. So now we are at equilibrium, but notice that the amounts are not the same. So there's much less over here than there is over here. So the amounts don't have to be the same to be at equilibrium, but the rate of exchange has to be the same.
means if I pour 140 into here, and I pour 140 into here, there's no difference. Okay, so I am now at equilibrium. Okay, so switching again, I can do this all day long. And from this point on, there will be no change in the volume in either tub, which means this reaction from reactant side to product side is at equilibrium. Okay, I can just keep right on doing it and nothing changes here. Again, we have 140 plus. This particular scoop happens to be actually less. in terms of what we have. Okay, it's not perfect with using scooping water, but again, we see 150 to 140, same amount of volume crossing over equilibrium. Okay, now in this case, if we look, we had equilibrium, so the process is at equilibrium. But if we look on the product side, we have much more water than we do on the reactant side. Okay, so in this case, because we end up with more product, we would call this a product favored equilibrium. We have less reactant, so it is not reactant favored. Okay, if you flipped it, and if you had a scenario where at the end you had something like this, this could be an equilibrium. It might mean you're using the big beaker for...
I'm going to say a word about this. In chemistry, as you move on in chemistry, you'll see that there's a mathematical relationship between the products and the reactants. It's really, the mathematical relationship is products divided by the reactants. So when you have less products and more reactants, you get a smaller fraction. So a small constant, equilibrium constant, would mean that the reactants are favored, like in this case. But if I had a lot of products and not very much reactants, and I divide products by reactants, it's like dividing 8 by 2, you get a ratio that's bigger than 1. So the bigger the ratio, the more product there is. The smaller the ratio, the more reactant there is, like in this case. We won't do math in this first introduction to equilibrium, but it will come in later lessons about equilibrium.
The product side and this little guy for the reactant side, and scooping over and over again. If that was the case, if you have very little product and a lot of reactant left over, this is a reactant favored equilibrium. Still at equilibrium, still flatlined, but we have no change in reaction rate there. Okay, so if we go back to the idea of the graph in our notes again, we see the bottom graph shows the amount, and in that graph, reactants were in red and products were in blue, I believe. So that was a product favored. So let's reset that to look like product favored, where once you've reached equilibrium, the rate of transfer, or how much gets transferred across, again, our rate of transfer would be equal. So that would come together on the graph, but yet the amount of product would be more than the amount of reactant. At equilibrium, this would be product favored, which represents the second graph in that slide.
And once again, equilibrium means equal rate of exchange, not equal amounts of stuff on each side of the arrow.
Okay, guys, that's the demonstration for this. We'll go back to our notes now. Thank you.
All right, so that is all I'm going to say about equilibrium. I just want you to know that it exists and it's applicable in lots of different areas of chemistry that goes beyond the scope of the course we've had in this first year. And you'll run into it in biology. In biology, there are all kinds of systems in the human body that work together to maintain equilibrium in our body. And I was trying to talk and write at the same time, so I'm going to rewrite that. The word I'm trying to write is homeostasis. And homeostasis is bodily equilibrium, where we try and maintain a constant temperature. It's a word that relates, it's an expansion of the concept of equilibrium in chemistry. The body does all kinds of different things to maintain a constant state. All right, so I'm going to stop the video there. There'll be a little quiz about it. It'll be qualitative, not quantitative. All right, thanks.